of dead people.
We have a 2% death rate and about, a very high infection rate. How many people will be infected and how many percent infected will die?
We can write some.
Actually, that's really
Yeah.
complicated. It is possible to.
I enjoy talking about, mass destruction, but if we start this sooner, we'll end it sooner, and then you'll have more time to work on the assignment that you're turning in today.
Excellent.
Okay. So we talked about relations. We spent quite a bit of time talking about equivalence relations. Remember, an equivalence relation is reflexive, symmetric, and transitive. And if you have an equivalence relation, then you can take a look at the equivalence classes, like the set of all things equivalent to some element. We know that the equivalence classes always partition the set, which is a fun fact. And we looked at a couple of particular examples, found some equivalence classes. Now we're going to look at partial orderings. And a partial ordering is a relation. It's a relation that is reflexive, anti-symmetric, and transitive. So just replace symmetry with anti-symmetry, and you go from an equivalence relation to a partial ordering. So we're going to let X, big X, be some set. And we're defining a relation, which we're using this symbol to denote, and it's going to be, and we're using that symbol because it's going to have its usual meaning. We're defining that relation on the power set of X, so the set of all subsets, by the usual meaning. And we're going to verify that this is a partial ordering. So, is this reflexive? So let's let A, the set A, be an element of the power set of X. And if you're in the power set, if you're an element of the power set, that means that you're a subset of X. We want to show that A is related to itself. This is, I'm just going to say it, obviously true. What I'm going to write down, nobody is going to think, like, why is that true? So
You're right now, duh.
I'm going to write A is a subset of A. A is contained in itself. So, because every set contains itself. So that means that this relation, subset, is reflexive. The next property to check is anti-symmetry. To talk about symmetry, you need to grab two elements. To talk about anti-symmetry, you also need to grab two elements. So we're going to let A and B be elements of the power set of X. So that means that they're both subsets of X. And for anti-symmetry, let's recall what this means.
It means there is no cases of symmetry at all.
Yeah. And if you're going to show that you have anti-symmetry, what you need to do is suppose you have an instance of symmetry. Suppose A is related to B and B is related to A, and then show that the only way that happens is if A and B are the same element. It was actually just an instance of being reflexive, of an element being related to itself. So let's suppose A is related to B. Suppose A is a subset of B and B is a subset of A. What does that mean?
Same thing.
Mm-hmm. We've used that all the time. In fact, that is the definition, basically, of two sets being the same. That's how we show two sets are equal, is we show that each contains the other. And so that means that this relation is anti-symmetric. And the last property, we're going to show that it's transitive. We need three elements, so we're going to let A, B, and C be elements of the power set of X. So again, A, B, and C are all subsets of X. What should we start out supposing to show that this is transitive?
Let A, B, and B.
So let's, so let's suppose A is a subset of B, and what else?
B is a subset of C.
We're going to show that A is a subset of C. And it's not hard, right? How would you show it?
Well, if B can be a subset of itself, or B is a subset of B, and B is a subset of C, then A must be a subset of C.
Well, that's the argument we're going to try to make.
You show it by circles.
Yeah, I mean, they could sort of illustrate it by circles. So I'm gonna start this out the way we do a usual containment proof. I'm gonna let little x be an element of A, and since we know A is a subset of B, then little x must be an element of B. What am I gonna say next?
Since B is a subset of C, little x must be
Mm-hmm.
C, and you can say little x is an element.
Yeah. So we said let x be an element of A, and then we concluded that x has an element of C, and that means that A is a subset of C. And that means that the subset relation is transitive. So we have this relation called a partial ordering. And that suggests that maybe there are other orderings. What makes this partial instead of total? There is another relation that is a total ordering. And actually, before I talk about the difference, let's think about the last one we just did. Let's suppose our set X consists of these integers 1 through 5, and we have the set A is 1, 2, 3, and the set B is 2, 4. Is either set related to the other? And of course, for that last relation, what we're asking is either set a subset of the other?
B is a subset of A.
So
No, it's not. No,
okay.
B is a subset of X. They're both B subset of X.
They're both subsets of X, right? That's what makes them kind of candidates, right? They're in the power set of X. But like, yeah, like 1, 2, 3, like that set A is not contained in 2, 4 because 1 is in the first set but not the second set. Also 3, right? 1 and 3.
Yeah.
But going the other way, that's also not contained in the set 1, 2, 3 because the set on the left contains the element 4, which is not on the right. So the whole containment, there is a natural ordering to that, right? Like it seems like there's a sort of a hierarchy, containment, but it's not a perfect kind of ordering because we would say that these two subsets, like these two elements of the power set, we'd say they're not comparable. I can't say I have the relation going in either direction. So there is a sense of ordering among those elements, but it's kind of not perfect. It leaves out some comparisons that we could make. If you have a partial ordering, but no matter which two elements you pick, you can always say that they're related in one direction or the other. That's when you have a total ordering. Is when every pair of elements you grab, like you could say they're definitely like related in one order. They are comparable, we would say. An example of a total ordering is just the relation less than or equal to on the real numbers. So we showed in example something 433, right? We showed that this relation is an reflexive, antisymmetric, right? Reflexive, antisymmetric, and transitive. We didn't use the words partial ordering then because we hadn't defined it, but that means it is a partial ordering. So that's enough to get it to be a partial ordering. Can we go a step further? Is every pair of elements comparable? In other words, if I grab two like random, real numbers, just grab a couple of them. So for every pair of numbers, elements A and B in the reals, will you always be able to say will you always be able to say that either A is less than or equal to B or B is less than or equal to A? Like, does one of those two things have to be true? Yeah. Right? I mean, look, you just place them on the number line. One will be to the left of the other. Or maybe they're the same number, but that satisfies the or equal to. So this gets a big old yes. So it's a partial ordering where every pair of elements is comparable, and that means it's a total ordering. A total ordering is also called a chain, which kind of makes sense. It's a complete hierarchy, like linear, right? The subset partial ordering, you kind of have orderings going in this direction or that direction, but sometimes you can't draw the line between a couple elements. Like up in the example above, there's no line to draw. Like we can't place one set kind of above the other in this example. Questions? Okay. All right, so as promised last time, I'm giving you the rest of the class time to work on assignment 4. That's due today. So hopefully maybe you've had a start on it, but you can work together. I'll be around to ask questions. So give a shout. Alan, you weren't here at the beginning. I have notes to hand out for chapters 5 and 6. In the event that they close the campus down, we'll be able to have class via Zoom, and I'll communicate with the class via Canvas about that.
I don't mean to be nosy.